At some point in your life, you made a decision that could have gone the other way. You stayed, or you left. You said yes, or you said no. You took the job. You didn't take the job. You picked up the phone. You let it ring. And somewhere in the quiet moments, late at night, or in the middle of an ordinary afternoon, you've wondered what life would look like if you had chosen differently. According to one of the most rigorously developed and widely discussed theories in modern physics, you didn't just wonder. You lived it. Right now, in a branch of reality that's separated from this one at the moment of that decision, there is a version of you living the other choice, fully, completely, with no awareness that you exist. This is not science fiction. It is not metaphor. It is the literal implication of an interpretation of quantum mechanics that was first proposed by a Princeton PhD student in 1957, and that is today supported by some of the most respected physicists alive. And the reason it hasn't been proven yet is not that the evidence is weak. It is that proving it may be the hardest experimental challenge in the history of science. To understand why parallel timelines are a serious scientific proposition, you need to understand the problem that forced physicists to consider them in the first place. Quantum mechanics, the physics of the very small, of atoms and electrons and photons, is the most precisely tested theory in the history of science. Its predictions have been verified to 11 decimal places. No theory in any field ever has been confirmed with greater accuracy, and at its core is something that has disturbed physicists for over a century. Particles, before they are observed or measured, do not have definite properties. An electron does not have a definite position. It has a probability of being in many positions simultaneously. It exists in what physicists call a superposition, a smeared-out cloud of all its possible states at once. This is not a limitation of measurement. It is not that the electron has a position and we just can't see it. Experiments have confirmed beyond any reasonable doubt that the electron genuinely has no definite position until it is measured. The moment measurement occurs, the moment any interaction with the outside world happens, the superposition collapses. The electron snaps into one definite state. The other possibilities vanish. Or do they? That question, what actually happens at the moment of measurement, is called the measurement problem. It is the central unsolved conceptual puzzle of quantum mechanics. And the answer, a Princeton graduate student named Hugh Everett III proposed in 1957, is the one that changes everything. Hugh Everett III was 27 years old when he submitted his doctoral thesis at Princeton University. His supervisor was John Wheeler, one of the most influential physicists of the 20th century, the man who coined the term black hole. Everett's proposal was radical enough that Wheeler spent months trying to convince him to soften it before submission. Everett refused. His argument was straightforward, and its implications were staggering. The standard explanation for what happens during quantum measurement, called the Copenhagen interpretation, says that the wave function collapses. The superposition ends. One outcome occurs. The others disappear. Everett pointed out that the equations of quantum mechanics contain no mechanism for this collapse. Nowhere in the mathematics does a superposition simply end. The equations describe all possibilities evolving simultaneously, continuously, without any special event called measurement that terminates the process. His conclusion was that the collapse doesn't happen, ever. Instead, every time a quantum event occurs, every time a particle could go left or right, decay or not decay, spin up or spin down, the universe does not choose one outcome. It produces both. The wave function does not collapse into one reality. It branches into two. Each branch is equally real. Each branch contains a complete, consistent, fully physical universe, and the observer in each branch has no awareness of the other. This is the many worlds interpretation of quantum mechanics, and its implication, followed to its logical conclusion, is this. Every quantum event that has ever occurred in the 13.8 billion year history of this universe has been branching reality into multiple copies. The total number of parallel branches is not just large. It is, by any conventional measure, infinite, and somewhere in that infinity, in a branch that diverged from yours at a specific moment, during a specific decision, or a specific event, or a specific heartbeat, there is a version of you that is still alive, still present, still reading something completely different, having made a different choice at the fork. In 1935, the Austrian physicist Erwin Schrödinger, one of the founders of quantum mechanics and a man who was profoundly uncomfortable with where his own equations were pointing, devised a thought experiment that has become the most famous illustration of the measurement problem. Imagine a cat sealed inside a box with a small amount of radioactive material. The radioactive material has a 50% chance of decaying within 1 hour. If it decays, a detector triggers a mechanism that kills the cat. If it doesn't decay, The cat lives. After 1 hour, without opening the box, what is the state of the cat? Standard quantum mechanics before Everett said the cat is in a superposition, simultaneously, alive and dead. Not one or the other. Both, until the box is opened and observed. Schrödinger intended this as a reductio ad absurdum, a demonstration that something must be wrong with the theory. Cats cannot be simultaneously alive and dead. Therefore, the theory must be incomplete. Everett's response was the opposite of what Schrödinger expected. He said, the cat is simultaneously alive and dead. Both outcomes are real. When the box is opened, the observer does not collapse the wave function. The observer becomes entangled with it. The universe branches. In one branch, the observer sees a living cat. In the other, the observer sees a dead cat. Both observers are real. Both cats are real. Neither branch knows the other exists. Schrödinger's thought experiment, designed to expose an absurdity, became the clearest illustration of what Everett was proposing, not a reductio, a description. The most common objection to many worlds is immediate and obvious. If parallel branches exist, why don't we see them? Why does our experience always contain one definite outcome, instead of a superposition of all of them? The answer came from physicist Wojciech Zurek at Los Alamos National Laboratory, who developed a framework called decoherence through decades of work beginning in the 1980s. Decoherence is the process by which quantum superpositions become undetectable in large, complex systems. Here is the mechanism. A single electron can maintain a coherent superposition, genuinely being in multiple states simultaneously, because it is isolated from its environment. But the moment it interacts with another particle, that particle becomes entangled with the superposition. And when that particle interacts with another, the entanglement spreads further. In a macroscopic object, a cat, a human brain, a measuring instrument, the superposition becomes entangled with an astronomical number of environmental particles almost instantaneously. The result is that the different branches of the superposition lose their ability to interfere with each other. They become, for all practical purposes, separate, isolated from each other, unable to interact or recombine. This is why you never experience yourself in a superposition, not because the branches collapsed into one, but because decoherence makes each branch effectively invisible to the others, sealed off by the sheer complexity of the environmental entanglement that occurred in the fraction of a second after the branching happened. Zurek's decoherence framework is not disputed by mainstream physics. It is experimentally confirmed and widely accepted. What remains debated is its interpretation, whether it proves that the other branches are real, as Everett claimed, or whether it simply explains why we can't see them without settling the question of whether they exist. Many worlds is not a fringe position. It is not the belief of a handful of eccentric theorists on the edges of the discipline. In 1995, physicist Max Tegmark at MIT, one of the most cited cosmologists in the world, conducted an informal poll of physicists at a quantum mechanics conference. Many worlds was the most popular single interpretation among the respondents, more popular than Copenhagen, which had been the default for half a century. David Deutsch at the University of Oxford, the physicist widely credited as the father of quantum computing, has argued for decades that the existence of quantum computers is itself indirect evidence for the many worlds interpretation. Here is his reasoning. A quantum computer solves certain problems by performing calculations across multiple states simultaneously. For problems of sufficient complexity, the number of simultaneous calculations required exceeds the number of atoms in the observable universe. The computation cannot be happening only in this universe. It must be happening somewhere. The parallel computations, Deutsch argues, are occurring in parallel branches of the wave function in the other worlds that Everett described. Sean Carroll, a theoretical physicist at Johns Hopkins University and one of the clearest scientific communicators of his generation, published a full defense of many worlds in his 2019 book, Something Deeply Hidden. His position was unambiguous. Many worlds, he argued, is not just one interpretation among equals. It is the most natural, most mathematically honest reading of what the equations of quantum mechanics actually say. The reluctance to accept it, Carroll suggested, is not scientific. It is psychological. The universe implied by the equations is too strange to accept comfortably, and so physicists have spent a century constructing interpretations designed to avoid the conclusion the math keeps pointing toward. Here is where many worlds stops being abstract and becomes genuinely disturbing on a personal level. In 1997, philosopher and physicist Max Tegmark described a thought experiment that has been discussed and argued about ever since. He called it quantum immortality. The argument runs as follows. If many worlds is correct, then every quantum event that could kill you also produces a branch in which it doesn't. Every heart attack that could be fatal also produces a branch where the electrical signal fires slightly differently and you survive. Every car accident produces a branch where the timing was 1 second off. Every terminal diagnosis produces a branch where the biopsy came back clean. In the branches where you die, there is no observer to experience the death. Experience requires a surviving consciousness, and in an infinite branching universe, there is always a branch in which you survived. The implication, deeply uncomfortable and impossible to verify from the inside, is that from the perspective of subjective experience, you never die. You cannot experience non-existence. You will always find yourself in the branch where you continued. Tegmark himself has been careful to note that this does not mean you are safe. In the vast majority of branches, people who take lethal risks die. From the outside, from the perspective of everyone who knew them, they are gone. The comfort of quantum immortality, if it exists at all, is entirely subjective and entirely private. It offers nothing to the people left behind in the branches where you didn't make, but it raises a question that no one has been able to dismiss cleanly. If your subjective experience genuinely cannot terminate, if consciousness always finds itself in the branch where it continues, then what you experience as your life is not the only story being told. It is the one branch out of an enormous number where you kept surviving long enough to be here. The most serious scientific objection to many worlds is not that it is implausible. It is that it appears to be untestable. If the branches are sealed off from each other by decoherence, if no signal, no particle, no information can cross from one branch to another, then how could any experiment in this branch detect the existence of the others? It is a genuine problem, and it is the reason many physicists who find many worlds mathematically elegant still hesitate to fully endorse it. A theory that makes no unique predictions that could distinguish it from its rivals is not, strictly speaking, scientific. But the search for a test is active. In 2020, a team of researchers, including physicists at the Perimeter Institute for Theoretical Physics in Canada, proposed a theoretical framework for an experiment that could, in principle, distinguish between many worlds and single outcome interpretations by examining quantum interference patterns in systems of sufficient complexity. In 2022, physicists at the University of Vienna, led by Anton Zeilinger, who won the Nobel Prize in Physics that year for his work on quantum entanglement, conducted experiments demonstrating quantum entanglement across distances and conditions that push the boundaries of what single outcome interpretations can comfortably accommodate. The experiments do not prove many worlds, but they progressively constrain the alternatives. Every result that is consistent with the full, unmodified equations of quantum mechanics, without collapse, without hidden variables, without additional mechanisms, is a result that is consistent with Everett's picture. David Deutsch put it this way: the burden of proof, he argued, has quietly shifted. Many worlds does not need to prove that the other branches exist. It only needs the equations to remain unmodified, which they have, through every experiment ever conducted. The burden now falls on single outcome interpretations to explain what mechanism causes, collapse a mechanism that has never been observed, never been measured, and finds no expression anywhere in the mathematics. The branches may be undetectable from within, but the equations that demand them have never once been wrong. Hugh Everett III published his many worlds thesis in 1957. The physics community largely ignored it. He left academia, went to work for the Department of Defense, and spent much of the rest of his life drinking heavily. He died of a heart attack in 1982 at 51, never having seen his interpretation taken seriously in his lifetime. His daughter committed suicide years later. She left a note saying she hoped to meet her father in a parallel universe. That detail has no place in a physics paper, but it belongs here because it is a reminder that these questions are not abstract. They are not confined to equations on a blackboard. They touch something in us that science has not yet learned to fully address. The possibility that every version of your life is happening somewhere. That the roads not taken were taken just not by the you that is here. That the people you have lost are not lost in every branch. That there is a version of reality in which the worst thing that ever happened to you did not happen. Whether that is true depends on equations that are a century old and still perfectly intact. Equations that have never once been wrong. Equations that describe, without ambiguity, a universe that branches at every quantum event and has been branching since the first second of existence. The science does not yet know how to reach the other branches. It does not yet know how to see them, or confirm them, or speak to what lives inside them, but it knows the mathematics, and the mathematics has never needed our permission to be true. Click the subscribe button for more bewildering findings like this. I'll see you in the next one.